And the session is sponsored by, as you can see, I'm now reading of the Ministry of Environment. No, I can't say the name of the session, so you'll see it in a second. Okay, this is a session of improving energy efficiency in climate and ozone-friendly refrigerants. So now you know the title, and I have learned it too. Sorry about that. I should be serious. Let's now try to start. Unfortunately, I'm in the chairing committee, and I'll be the first speaker. And I had selected to speak in English. Even you obviously see Serbian is my native language, but it is better to use something much more international than Serbian. Although in Serbian culture, for our international guests, there is a saying, speak Serbian so that everybody in the world can understand you, which is supposed to be a joke, but anyway. So let's start. First of all, I have been asked by organizers to point out that there is a new application which is called Match About. And that application, if you have downloaded it, is good to ask the question, give a comment, whatever you want to communicate. Of course, after the presentation, you'll be having a chance to ask the question immediately in a kind of old-fashioned way. Slovo main, can we start? Okay, so we are ready then to start, and I'm now, as I said, in an interesting situation of how can we go to the presentation mode. I should close this, or I will try to push it down. And this is my presentation, and I will start this presentation this way. Okay. My presentation will be very short. I think and I hope I will wake you up, and I think that you will like it. Oh, it is there. For those of you who don't know me, I'm Pega Karnjak. I have at least 3 hats. One is I'm professor of mechanical engineering at the University of Illinois. I'm also director of the Air Conditioning and Refrigeration Center, which is industry university cooperative center, research center at the University of Illinois, and probably the largest of its kind in the world. And I'm also founder and president of CTS, Creative Thermal Solutions, which is really vibrant, 50 very highly educated and very highly motivated engineers with objective to do contribution in research and product development in mostly environmentally friendly and energy efficient and cost-effective solutions. Today, I will maybe this is this. This is this. Oh. Okay. Okay, sorry. So as you now I should be watching because this is not working here. Oh, this is portable microphone. So I'll be watching this. Yeah. I'll be what? Can you hear? We should have tried all of this before the session. Can you hear me now? No. It's not good when the morning starts with technical. Okay, let's ignore technical difficulties. We had also difficulties in developing this interesting project. How many of you believe that transcritical CO2 systems can be equally efficient as, let's say, R22 or 407C system? I would say nobody most likely believes in something like that. And we have been able, not the first time, many times, to show that it is possible to have a system operating in transcritical CO2 mode to be more efficient than using conventional refrigerant. And that fairy tale is what I'll be telling you today. Hi, guys. Okay. That story will be about the train air conditioning system. In high-speed trains, as you know, Chinese are trying to penetrate everywhere, and Chinese companies came to me and asked whether they can have a transcritical CO2 system, because that's the only way, quite frankly, how they can come to Europe and sell their trains. Because there is no way that with any other solution they will be let in Europe. And that's the biggest potential market for them, and if they have that solution, they hope, they believe that they will have kind of a key to some other markets. That's the motivation for the project. Now I'm first introducing to you how that looks like. This is like the train, high-speed train, and there are various designs of air conditioning systems. And now I was looking very carefully wherever I go, in subways, metros, in trains, in high-speed trains, how people design these systems, much more than I was looking into that before. So this here on the top left is our baseline, the way how it looked when it came to us. The system was supposed to make 44 kilowatts at rating condition, which is ambient condition. It's a 35 degrees C, and indoor condition is relatively high temperature, something around 27 to 29 degrees C, very, very high. And then I insisted to get the baseline system, the system that they use today. And they use 407C, and obviously the reason why they use 407C is that they didn't change too much from R22, and that was the simplest replacement for R22, and not to do too much in that. Here I'm showing some other designs. We have first taken the data for efficiency and the capacity at the rated condition at 407C. And we have gotten a lower capacity than they thought that they have, and we have gotten a lower efficiency that they believe that they have. But that's the reality. That's why I always wanted and always want in these situations to have some baseline to know where are we coming from. So we have put that system in our, oh, it works now. Can you hear me now? Yeah. Okay, perfect. So now I can watch from the same position as you. So this is that system which is placed in our condenser chamber. You don't see here, this is a return duct, and there is another return duct, and in the center there is a discharge air, cold air, that goes into the cabin of the train. And oh, okay, now I will do it this way. So this is the wind tunnel to measure airflow rate and to measure temperature at the discharge of a cold air. So the system is very simple, that we have designed for CO2. So we have here compressor, and there are two systems. These 44 kilowatts are divided into two 22 kilowatt systems. Everything is kind of to be redundant. And every solution in the train, especially in that type of a train, is extremely conservative. They didn't want to go to any microchannel. They didn't want to go to fancy compressors that I was suggesting, but everything to be kind of robust, as conservative as you can imagine. And maybe there is a good reason for that. And I was told that they are always thinking about what if that breaks, or especially if it breaks somewhere in a tunnel, on a bridge, or whatever. So now here you see compressor. We have one gas cooler. This is for 1/2 of a train. Internal heat exchanger. And this here is the evaporator, and it's a DX evaporator. Simple as it could be. And here is a diagram that we have used and designed that. And we have, of course, a little bit overrated that. And this is the capacity of an evaporator on a gas cooler. And we have gotten COP of 3 to expect with that type of equipment that we have originally thought about. And then we start designing that. And of course, you see here one side of a gas cooler, the other side, the evaporator is one, but it is divided internally into two evaporators. You can see here 2 compressors, and obviously you will see that we have been using several compressors until we have found the selection, made the selection. And we start looking into components. You see here a series of compressors that we have been looking into. Today, quite frankly, I would have chosen another compressor which wasn't available at that time, which is much lighter, and that always happens. Whoever is an engineer and had been working with that, you like everybody in everyday life, you pick from what is available, and you try to make a reasonable match. And then we have looked into good or better fans for the gas cooler and selected some. Obviously, you see here we have selected Bitzer compressor, but we have tried Frascol and Dorine, and we have tried Bock. This Bock was, quite frankly, the best option, but at that time they were replacing that design with another design of a compressor, but that's life. This is a selection of evaporator blower for the evaporator. Actually, there are 2 blowers like that, and I have selected pretty well-known companies, and nothing fancy about that. Then we have designed and built heat exchangers. The only interesting part is that when you go to higher pressure, and especially for CO2, it is better to have smaller channels, smaller pipes. And we have here selected 5mm tube, but we have had some special design in the heat exchangers. But then we redesigned the frame to be 13% smaller. So this is baseline frame, and this is the frame that we have redesigned. Can you imagine to make a CO2 smaller, greater capacity, and higher efficiency? You will see all of that just in a second. So then we have gotten these components and more of these, and we have built and put this in what we call breadboard system. It is called breadboard like when you have electronics and you put on a breadboard your components, connect with the pipes, and try to get capacity and efficiency. And you know that you will never get in a real system that high both capacity and efficiency as you get on a breadboard, because you have influences of non-uniform airflow rate or kind of difficulties of any kind that you can imagine. It's never better than in a breadboard that's here. So, and then after confirmed calculations, we fabricated the prototype. This is how that fabrication has been looking like. So you have these two fans, and then you maybe see it better than I see here. We have mounted evaporator here, put these blowers on the evaporator side, fans on the gas cooler side. This is a gas cooler, one of the compressor. And for the internal heat exchanger, of course, I would never use normally stainless steel brazed plate heat exchanger for internal heat exchanger in transcritical CO2, but this is the most robust you can imagine. So they were so obsessed with having robust and not necessarily the lightest or the nicest or the more creative approach. And then we have checked the performance in the same way, in the same conditions as baseline. So this here is just a description of the way how we have done it. So here you have gas coolers, evaporator, and the blower. Blower is blowing air to evaporator chamber. So battery is dying anyway. And the return comes to return of the compressor. Get the new battery would be good. Then we have tested that again, and we have gotten results. Okay, I think I should, maybe it is good to show you here. This is probably the key for engineers, the key slide. This is temperature enthalpy chart. I love temperature enthalpy much better than pressure enthalpy. Why? Because in pressure enthalpy you just see pressures, while in temperature enthalpy chart you can see everything what you see in pH diagram, but in addition you see temperatures, temperature profiles, and the deep difference between. These dotted lines are air temperatures, and you see here two colors. One color is blue for 407C, and the other one is black for CO2. You have this black is the dome of CO2, and this is 407C. So now you see the cycle black 4. So what you see here is blue is, as I said, 407C, and black is CO2. And we can see now many things. First of all, air inlet to the evaporator is shown here like 28 degrees C. This is the same air inlet temperature to both evaporators. As you can see, more capacity with the same airflow rate, because we have the same airflow rate, this requirement for the train. This here indicates much more capacity. Black line, air, in CO2 system is cooled to the lower temperature than for a 7C system. And then in the condenser or a gas cooler, we start from a same temperature of 35 degrees C. And this here is air inlet to the condenser and air outlet, air inlet and air outlet from the gas cooler. Of course, this is a simplification. Airflow is presented as, these two heat exchangers are presented as counterflow heat exchangers, which they are not. They are cross-flow, overall counterflow, but cross-flow really. But anyway, it gives us some indication. Look at this. What can we learn from this, this chart? We see higher evaporation temperature with CO2. For the actually lower temperature of air, clearly that means that the performance of evaporator is significantly better in the CO2 system. Why is that so? The surface area is almost the same. That is not the problem. One of the problems is existence of the superheat, and pretty high superheat in 407C evaporator, but that's how they operate it. In transcritical CO2, you have to have accumulators, so basically your evaporator is flooded. So evaporator is not flooded, but slightly. You don't need to have superheat. There is one thing. The other one is there is an internal heat exchanger here, that internal heat exchanger will take care of any potential droplet that is coming out of your evaporator. That is also, you shift a little bit the evaporation in internal heat exchangers sometimes if you have problem with the maldistribution. Thermodynamically, evaporating in internal heat exchanger doesn't make any sense. But it could practically improve the performance of evaporator because it is then higher heat transfer coefficient in that situation, overall higher heat transfer coefficient. Okay? So now when we look into this, we also can see following things. Much better performance, as I said, of the evaporator, but look what we have done on the left side of a diagram. Exit from a normal condenser is somewhere here, and that condenser operates at 50 degrees C, more than 50 degrees C. Even the pressure drop is so high that you can see here. This, when you look now into these two isenthalps expansion process, they are almost on the same line. And this is well known that this is really the weakest point, one of the weakest points for the CO2, because due to low specific heat of liquid in CO2, we always end up somewhere here at much higher inlet qualities to the evaporator, and that is extremely expensive from efficiency point of view. But we have, with very good gas cooler, well-designed gas cooler, equal size of the gas cooler, actually smaller volume, we are coming to like 2-3 degrees C. This is inlet, this is outlet temperature, 5 degrees C. Approaching temperature difference. So this is exit from the condenser, CO2, and inlet air. So this is the measure of effectiveness of the heat exchanger. So that is why, and look at this approaching temperature difference. When you do analysis, and that is one of the major problems why people don't understand how you can make CO2 to be better. Because everybody in the modeling assume that the exit temperature difference, or what we call it approaching temperature difference, in let's say 407 or 410A, whatever, refrigerant will be the same in CO2. No, it is not. And it is also not because we have done a very good design of the gas cooler. But that is the reason. There is no magic. There is no miracle here. And then we have a pretty significant internal heat exchanger. And look how much we came to 30 degrees C exit from, or liquid inlet to the expansion device. And then the quality here is pretty low. So that helps dramatically. That is why we have so good performance. So I'm not showing you what have we done, but I'm explaining how this is done. So there are no miracles. We engineers don't believe in miracles. We make maybe something that looks like a miracle to others. Okay, so what I haven't said here is instead of 37.9, we got 44.7 kilowatt capacity. Instead of 1.9, we got 2.3 COP, significantly higher than what is the baseline. Now, if you remember, I have showed you a little bit over 3 there. We expect it to be 3, but it's not 3, it's 2.3. There is a plenty of room, and we know exactly where we can tweak it in the next stage. But this was way more than our customer had expected. They are extremely happy with that, and compressor also was one of the reasons. Always, CO2 compressors are more efficient than any other compressor. It is not because design is so much better. It is because the fluid is such that it provides opportunity for higher efficiency. Because the pressure drop through the valves, if you have valves, and here we have valves, and some compressors don't have valves. You have lower pressure drop, and so on and so forth. Now, in the last slide, I'm showing this saying here, the first 8 systems are in the trains and during the real-world testing. This is assembly line in Changchun in China, where they put these systems together, and it is now running over there. And our CO2 system is much higher in capacity, much higher in efficiency, and 13% smaller volume. Wow. Does it mean that CO2 is better than 407C? By no means. By no means. It just means that we know how to make CO2 system much better than they had known how to make 407C system. That's also another truism in life. Yeah, if you know how to make it better, make it, and it will look well. So with this, I will stop and be open for any question that you may have.
Hvala profesoru Krnjaku na ovom lepom predavanju. Izvinjam se zbog ovih tehničkih problema, ali nadam se da ćemo sada, da smo rešili te osnovne tehničke probleme.
And we already got first,
mi imamo neko pitanje, izvolite.
I see. What is the criteria for saying Bitzer was the best compressor choice? That's a very fair question, because I'm sorry. Very fair question. I am too easy when I say something was better than the other, and it is good to be kind of reminded that things are not so simple as they appear to be. What is the best choice? You try to find, first of all, to have a good size of the compressor, and then good efficiency, then good weight of the compressor. It was very important for us to have a very light compressor. Unfortunately, none of these compressors is a good choice for this particular application. Why? Because all of them are semi-hermetic. And we were competing with a hermetic compressor in the baseline. So we had to try to save in weight on some other ways. So this was the lightest compressor, not by far. Now, the other compressor that was very, very light and would have been, quite frankly, better selection for us is this compressor. If someone, and there is another bulk compressor, there is a radial compressor. Those of you who have followed, for instance, automotive development, automotive CO2 development, maybe remember when Aubry's compressor, they have a 5-cylinder radial piston compressor. That was the lightest of all compressors. And even now, the new design like that is really the lightest. And we were just not in a good moment when we were designing our system. So that is the reason why we had selected that compressor. Yes, please.
I just would say that you said Bock is the best, but are you looking at the COP or? Because
wait.
Here
Wait,
Copland have a far way best COP.
Yeah, motor weight.
2.7, Bock 2.23, and Bitzer something like 2.
Have you seen what is isentropic efficiency? These are ungodly. I even don't believe that we haven't made a mistake in calculating like 80%. We have normally seen their compressors around 60, 70%. And I don't sell Bitzer compressors, by no means. This was, the criteria here was the weight. That was the criteria number 1. And number 2 was a good isentropic efficiency. And difficult now to tell you, I know isentropic efficiencies for all of them because we have tried all of them, but it is maybe not fair to reveal all of that. Yes? Risto. Professor Risto Tsisonkov.
Yes, you compare CO2 units. You compare CO2 units with conventional air conditioning units with R407C. And in both cases, you put expansion valve because compared to be equal. But what do you mean if you put ejector in the CO2 system? Additional improvement will be sure?
Absolutely. And we have been among the first in the world to work in ejectors in CO2, but there was no need here to use ejector. You don't use all of your tools from a toolbox when there is no need for that. You just use as much as needed to come to the goal that is put in front of you. We are waiting for another project or another projects, and we know how to make it much better. Fair question, correct. Thank you very much for the question. Yes.
Did you plan it for that train? Two independent refrigerating systems. Two independent.
Yes, two independent refrigeration
How many
systems.
people can be seated in that train?
Wow.
Because of, no, I'm asking because of that capacity, 44 kilowatts. I think.
Can we please use the microphones? The translators cannot hear what you're saying.
The question was, what is the number of people in the train to compare the capacity of 44 kilowatts for one whatever car in the train? Honestly, I don't know.
Okay.
Sorry.
Thank you for the presentation, very interesting. I got the impression that the baseline unit was very close to being an old R22 unit with motor 7C put in.
Absolutely.
Do you have any idea if any of the competitions offer a more, let's say, optimized for newer conditions? So maybe the baseline was a bit unfair?
Yes, I'm aware of that. The question was whether there is a better baseline than that we have had. Yes, I'm aware of that. I'm also aware of the fact that some other people have tried to. There is another company that have asked another Chinese R&D center to develop the same thing. And they haven't even come with the same baseline to the same COP that we have achieved. Yes, there is no question there are better systems, and believe me, I also know how we can make our system much better. One of the directions is what Professor Tsisonkov said, is to use ejector, which we haven't. I know what we need to do with the heat exchangers. I know much better compressor than we have. Things about these comparisons, this is always a moving target. We have that experience with many technologies. It's not only now for train. We've been doing that over decades for car systems. And this is phenomenal benefit for the industry. There is phenomenal benefit because technology in the car, for instance, I'll give you an example, in a car air conditioning systems, efficiency had doubled over 15 years, doubled, because we have measured the first systems when efficiency wasn't the problem. When CO2 came in, those who were against CO2, they were saying, oh, this is so bad fluid, you cannot do anything with it. And then we have shown that we can do better than 134A in car air conditioners. Then they said, oh, we can now make our 134A system better. And they did. And we worked on the same project to improve 134A. And then we said, okay, now let's go improve CO2 again. And you go that, and this is kind of a process that lasts. And I think that this is happening in industry, in science, everywhere. We learn, we improve, and then the other competition do the same thing, and we come and do better our part. But my point is, we have from a get-go made this better. And obviously you see that there are so many other things how to improve it. So let's go further. You know, that is the way how things go. We need to. Oh. What is the volume of CO2 used per unit? And are there any losses in refilling needed during operations? Okay. That's a very fair question. That was one of the weak points, and it is still for automotive systems because they vibrate here. This system vibrates, but we haven't installed any hose or anything like that. The user doesn't like that, and we have just made elastic pipes that give us sufficient movements. Now, in all honesty, I need to tell you that some of our first design had failed, and pipes got broken, and then we had to fix that, and we have fixed that, and it works now, and so we don't have leaks right now. Indeed. If the outdoor heat exchangers get very dirty, will the fall? Yes, we're worse for CO2 than 407C. Good question. I would even say that 407C would maybe have even higher sensitivity to that. Here is why. You know, CO2 is very bad in two parts compared to conventional refrigerants. One is this here, because we compress to much higher pressure and to much higher temperature. We believe in thermodynamics. And thermodynamics tells us that whenever you go to higher pressure and to higher temperature, you will need to pay in generated entropy. There is higher work and so on. This is one of the, So this here is one of the weak parts. So, but that weak part, we have improved. Actually, we are taking that in as an advantage, because in cycle analysis that is not seen as an advantage, because the size of the heat exchanger there doesn't matter. But look at this temperature difference here. This temperature difference here is significant. 90% of heat is transferred in 10% of the surface area in the gas cooler. So from that point of view, I expect less sensitivity. From this side, these other 90% of surface area has to do something here. And as low as we go with the exit temperature from gas cooler, it is better for the system efficiency. Rule of thumb, every degree C that you can go lower, this is something about 7.5% of efficiency. 1 degree lower, 7.5% of efficiency. Huge. Now, what Andy is saying is, when we reduce the flow rate, what will happen? Then this line will go like this due to fouling of the heat exchanger. We will have a lower air flow rate, so this inclination will be higher, and maybe we will have to go higher with this exit temperature. That would be that would detrimentally affect CO2, and maybe more than that. Yes.
It's a notorious problem for railway, particularly for air conditioning units. But I think a focus should be on making the unit more easily cleanable to bring it back to the as new condition, which the existing units don't do so the dirt just gets built up and built up and built up. You can wash the train, but you're just pushing the dirt further into the heat exchanger. So if you design your unit to be cleanable, you can retain the better advantage.
Yes, yes, absolutely. I 100% agree with that. Maybe that is one of the reasons why the customer didn't like microchannel heat exchangers, but they like conventional round tube. Not much enhancement on the fin side, because fin here is not extended at all. And I think maybe I'm taking too much time. I should. Okay, now here is another. What was the criteria for staying busy or no? Oh, I have finished.
Mislim da nemamo više vremena.
Okay, we need to stop. Thank you very much for great questions.